All right, discrete math, welcome. Here we go, Friday afternoon. People are at the ARML, doing the math. Math going on here too. We are going over the homework on regular grammars. Let's go. Number 5 presented us with a regular grammar. And here is the grammar. And basically gave you a whole bunch of strings and said, yo, are these strings part of the language generated by this grammar or not? And you had to make the actual, you had to produce the derivation. And here, like, yeah, dude, we do it. B, impossible. What was B again?
It was 101.
101. It appears that we just like straight up can't make a 101 because the only way to make a string start with a 1 is to go S goes to 1Y, but then Y just can only make 2 zeros or a 1. It can't make just 1 0. So good. Anyway, etc., etc. We're gonna blitz through this homework. So D and C, D, and E can also each be made, like C board for the derivation. Good. 6 was more of the same. They gave you a grammar and asked for strings. Strings C, D, and E can it be made or not, and give some reason why it cannot. For part C, that was the string BBACAB. There's the derivation. For D, we want BBAACB, but we just like can't do that, man. Because at each step,
there's only one choice.
There's only like one choice as to how to get that character, and eventually you get with the BBAAX, and you just can't, from X you can't get a C. So you just like can't do it, man. And E is like similar. All right, 7A gave a particular grammar up there on the board and said like, what can we get out of this grammar? Just throw an answer.
B plus B is redundant, I think.
Period 5 got this wrong. No, you do need it. I think.
Why?
Because there have to be 2 B's. For 7A, I got exactly what this person got. And for 7B as well. Yeah, I thought this was like a little. Do you want to like do 1 or 2 of these? I think we should do 1. Which one do you want to do? 7A or 7B?
7A.
7A is more interesting? Okay, I think Randall's picking the easier one because he wants me to go as fast as possible. But we can make like a tree of all possible derivations, like ish. So what does it look like? We start with our start symbol, and we have 2 rules to follow. We can follow the rule that S goes to AX, or we can follow the rule that S goes to BY. And then someone make vaguely sure that I'm in frame. Following, what do I do with this rule X? Well, I can either just end it with a C, in which case I have the string AC, or I can replace X with AX, in which case I would have AAX. And then again, I can end it by replacing X with a C, giving me AAC, or I can replace the X with an AX, and then like, etc., etc. Okay, so it appears from the left-hand side of this tree that all of my strings are going to have at least one A followed by a C. So that's what A plus C. And then on the right-hand side, if we have B, if S goes to BY, well then what does the Y rule do? Y either ends it with a B, in which case we have BB, or Y gets replaced with BY, so we get BBY. And again, either I replace the Y with a B, so we get BBB, or I replace the Y with like a BY, so etc., etc. And so all of these strings are going to be a bunch of B's, but at least 2 of them. Hence, like the B plus B. Cool? Say cool. Woo! 7B is like more of the same. It was actually a little bit harder, but I think that is the right answer. Any objections? Nope. From the class, no objections. Perfect. That's what you got? For 7B?
Yeah.
Good. Okay. 9A. Let's do a little zoom action if possible. 9A. What's going on? What did you have to do for this problem? You also had to like write. Oh, you had to write a grammar, right? I think. Yes. You have to write, your language is the language in which there is no BB in the beginning. So let's see, this person says this, who is doing this? Is this Ezra? No, not. Now it says, okay, here's my plan. I have to just avoid there being a BB. So first off, I could just have an A, man. That could be the whole string. Or I could just have a B. Or we could have the empty string as well.
Wait, the empty string isn't included. I did forget one.
Why is that not included?
Because it's not included in the...
Oh yeah, now we're getting into this again.
Philosophical discussion.
It's
implied.
Because they included it in later
The
problems.
answer is it's implied.
Okay. Because
Yeah, I think Gossett has
included it in
yeah,
later
that's right.
problems.
Yeah, I think that Gossett has performed some philosophical disservice by making a language meta-language distinction, where he messed up the distinction basically. I think we should call this set the alphabet, and that is the set of characters which may appear in the string. Okay, and then I think the terminal symbols are necessarily all of these things plus this symbol, because that's what's needed to explain the grammar. Because this is a symbol which represents the null string, and in fact, you with me?
Yeah.
So I need the null string is a string, and so I need a symbol for it, and I need to be able to say things like this, and so I need it to be a terminal character. But it seems wrong to include it in the list of terminal characters. I think it is implied always, because I need that expressive power given any alphabet to talk about the null string. So that's what I'm just deciding from here on out.
But you can totally write a grammar which doesn't have the null string in any of its rules.
I can write a grammar which, yes, some grammars may not have the null string, but I do not think it is appropriate to continuously explicitly mention that the null string is one of your terminal characters. I think it's better to simply introduce the alphabet and then to know that the null string is there always. Because intuitively, do you agree, Niles, that like the null string should be a string in this grammar? I mean, it is a string in this language.
Yeah, it makes sense. I saw he on
You got confused.
Yeah. On
Yeah.
some of the later problems though, he like included it. Which was
Because
confusing.
in some ways, it should be included as a terminal character. I agree.
Is it possible to do this problem without using lambdas in your
Yes.
rules?
Yes. If you say that lambda can set
Lambda must be one of the possible.
If the null string is a string in this language, and I claim it is,
Yeah.
then I need a way to be able to make this grammar generate that null string. And so therefore I need this character. And so it seems that we should just always have this as this is sort of like this is a terminal character, this is a terminal symbol which every regular grammar should have. I do not need to explicitly mention it. I think it's best to think of this as the alphabet. And then to define the set of terminal symbols as every character in the alphabet plus plus this character. With me?
Cool.
Woo!
Wait, also the axiom assumes existence. Like otherwise you wouldn't have that rule.
Yeah, there's all, I need the null string as part of this. It's like the same way I need the empty set, I need 0, I need those guys. Okay, woo! Good. What is actually happening here? Okay, so now it's saying, yo, you could just have an A, or you could just have a B, or you could just have nothing. Or you could have, you added one in, or you could have A, so you can write an A, and then you can go to big capital A, which is kind of like the state of I can do whatever I want next, right? And then, so from state A, I can just end it with an A, or I can write an A and go to the state of I get to do whatever I want, or I could write an A and...
I don't think A is the state of whatever I want. A is the state of I'm going to write an A next.
No, this is actually confusing me a little bit. B is the state, you're sort of doing it differently than I do. So you're thinking of B of the state of there's going to be a B next.
B next, yeah.
Okay.
This works, I think.
I think this works too. I think there's a shorter way.
Yeah, there is a shorter way.
I think there's a lot shorter way. Or somewhat shorter. But anyway, yeah, so B, from state B, you have to make a B next, I guess, right? That's what's going on.
Yeah.
And if you can either end it or you can make a B and go to A. A is the state of I have to do an A now, I guess.
Yeah.
Yeah, okay. So when I have to do an A, I either do an A and end it, do an A and go to the state of have to do a B, or do an A and go to the state of have to do an A. And if I'm in B, I can either do a B and then go to the state of have to do an A. So yeah, that avoids ever having two B's consecutively. Okay, I accept. What else is happening? Can we just like stop going over the homework? Good. This was like a cute little problem that said move 3, lower 3, yeah. So we need to create a grammar which generates a language which has more 3-character strings than 4-character strings. Well, one excellent answer to this problem is, dude, I'm making a grammar which has only one rule and which produces only one string. This entire language has only one string in it. That string has length 3. Thus, there's one string of length 3 and no strings of length 4. And every answer to this problem, I think, is going to be some sort of trolley-like type thing like this, right? Basically.
Is that the intent of this problem?
We have yet to prove 1 is greater than 0.
Good. Over to the other board, is that worth going over?
No.
And see?
No.
Good. Good, let's do some things. Let's flip this over. No, let's do it here. Okay. Yeah. So we have seen, here's where we are, vocab-wise. We have these finite automata, and they can be used to recognize certain strings, and they accept some strings, and they reject others. We also have regular grammars, which can be used to generate regular languages. We also have these things called regular expressions. Can someone make sure I'm in the frame of the camera? All right, what is a regular expression? All right, first of all, I have to say I don't know like too much about this. I know people who do a lot of like computer science like use these things all the time. So feel free to correct me if I say this a little bit wrong, but I think I know what I'm talking about now. All right, what's a regular expression? It's kind of like a search term. One way to think about it is like a search term. It's a way of searching through large bodies of text for certain kind of combinations of substrings. And it uses the notation that we learned yesterday. Okay, let me just jump right in. Suppose I have an alphabet ABC. Well, consider the following things, which I'm calling regular expressions. Here's one. It's A, B star, or C. So this is the or symbol, and it has the lowest precedence. Is that how I'm supposed to say it? Yeah. So that means we do that last. So there are implied parentheses around all this. Okay? So this, and the phrase to use is matches, substrings of the form, where there's an A followed by some number of B's, or there's a C. And so we have the following strings, A, B to the N, where N is greater than or equal to 0, and together with the string C. So any string in this set or this set, so this is the union of these two sets, is a string which will match this particular regular expression. Okay, and so let's do some more examples. So A, B star, or C. So when I want to like override the built-in precedence, then I use parentheses, of course. So what is the interpretation of this? Oh, and when they're just two characters next to each other, it's like concatenation, like yesterday, right? So this matches. Either you have an A, either followed by some number of B's or a C. So either, so it's the set of strings A, B to the N, where N is greater than or equal to 0, and just the string like AC. Cool. Okay, let's do a couple more. A, B, in parentheses, star, or C. This also matches some stuff. Well, now it's like A, B is like an A followed by a B, like some number of times, 0 or more times. So this will be like A, B to the N, some number of times. Any string that looks like that, or just, again, just the string C. So each of these are called regular expressions. They match a certain thing. Right? This is the one I find actually confusing, and it's sort of difficult to write any other way, which is sort of shows why we sort of need this notation. So this, when you have an A or B star, this is interpreted, you should think of A or B star as like meaning, well, we kind of know what it does mean actually, right? Because we defined this yesterday. We should think of it as A or B to some kind of power n, where that power might be anything. But like A, maybe I should do this. A or B, like cubed for example, means A or B times like A or B times A or B, or concatenated. And sort of like then you make the choice as to which one of these you want, right? So it's not like you make a choice first and you do it n times. You do the choice n times, each choice independent. So this matches like a lot of things. And I don't even know how to write it in sort of set theory notation almost without this. So because right, like the first character, well okay, first of all, what's the shortest string that could be in this language?
C.
Just C, right? Or we could have AC, or BC, or like AAC, or ABC, or BAC, or BBC, like et cetera, right? You could have, yo.
Never mind.
Cool. Okay. Good. What can this be used for? This can be used for a lot of things, but I think the way people use this, like in the real world, is when they want to like search through like a bunch of strings for like some stuff, and you don't quite know what it looks like. A famous example, which I thought I was being really cool and inventing during 6th period, but then when I Googled it, like there are tons of articles already about this. The spelling of Hanukkah. Notoriously difficult to spell. There are many, many, many spellings of Hanukkah out there. It's really, really annoying. I am myself Jewish, or was, or whatever, and I spell it like arbitrarily 10 different ways each time, depending on my mood and how I feel like. Alright, so suppose you have an extremely important email buried in your 100,000 emails where you talked about Hanukkah with somebody, and you needed to find that email. You have to search through like many, many, many times to find all the possible spellings. Or you can use regular expressions. Because, as we all know, Hanukkah sometimes starts with a C or sometimes with an H, right? Okay, so that means the C, the capital C is like optional. And so we go C or, this is like the null string, right? So because they kind of like put it there, or not. All right, and then followed by, there's always an H. So either it's like the lowercase h of the like, because we started it with the C, or the C wasn't there, and it's like a capital H. Although I think I might be screwing that up. I think we're okay.
I think it should be written as.
But here you can get C.
Yeah, maybe you're right. Yeah, I think that is better actually. So you're saying CH
Or
H.
or H. Yeah, that is better. And like right and stuff.
But
Okay,
you
good.
can get two capitals.
Then what's up?
With
Yeah.
the old version, you could get
Yeah, the whole version was kind of a little bit bad. Okay, so then we want an A, and then an N. All right, and then people also disagree about whether there are two N's or just one N, right? So then we need an N or nothing. And then, all right, the internet claimed there was some choice here, but I claim that's crap. This has to be a U. This is a U, and now there are some K's, either 1 or 2. So we throw in one K, and then we have K like or not. And then we always have an A, and then your question is whether you put an H on the end or not. Boom! Yeah, that's good stuff. So this is a regular expression, which if you, which will match any legitimate spelling of Hanukkah. Cool? Say cool.
Do you think all things this matches are legitimate spellings?
And I hope, if I've done it correctly, that all things this matches are legit spellings of Hanukkah. Yeah, I think, yeah. Okay, get it? Say good. Okay, so I'm going to turn the camera. There is a formal definition of this, which I kind of want to like skip-ish. Mostly skip, but I'll just kind of like very quickly go into it. The formal definition of regular expressions. I need to tell you what a regular expression is and how they work. Well, I want it to be, I need to do it recursively because a regular expression can be arbitrarily long. So there are the sort of base cases of the definition. The base cases are, first of all, just the empty set itself is a regular expression. And it matches nothing. Okay, then lambda is also a regular expression, which matches only one string, the null string. And A, any character from the alphabet, is itself a regular expression, which matches precisely that character. Okay, again, some like philosophical things going on here. Let's not choose to not talk about it. All right, and then there are the what does that say? Oh, the like recursive inductive cases, or then there's like the recursive part of the definition, recursive. And okay, basically it's like this: if A and B are regular expressions, then the following are also regular expressions: A, B. So the basically the concatenation of a regular expression and another regular expression is a regular expression. And what does it match? Okay, I don't feel like writing this, so I'm just going to say it in words. This regular expression matches any string which itself is the concatenation of two strings, one of which is something that A matches and one of which is something that B matches. Kind of exactly like I was saying. Yeah? Whew, I think I said that right even. A or B, if A and B are regular expressions, is itself a regular expression, which matches any string, which is either one of the strings that matches with A or one of the strings that matches with B. And finally, A star is a regular expression, which matches any string, which is like the concatenation of like 0 or more strings which A matches. Woo. Cool? Okay, that's actually way clearer than Gossett's explanation of what's going on, in my opinion. So you could read this section in the textbook, but it will mostly confuse you unless you already know regular expressions, I think. Good. How are we feeling?
Good.
All right, you also may have noticed that this notation we like borderline had to invent just to talk about the kind of regular languages that we were generating with regular grammars. Agreed? Which suggests that there is some deep connection, can you raise that, between all of these things. And there is. Jonah, as you were expecting, I think it was you that was saying this as we walked in, all these things are equally expressive. And okay, what do I mean by that? Let's go through the vocab once again. A regular grammar generates a language. That language we call a regular language. Yeah. Okay. For every regular language, there exists a finite automaton which recognizes all and only the strings of that language. It's a finite automaton that goes with every regular language. And vice versa. For any finite automaton, if you take all the strings that that finite automaton recognizes or accepts, we should really say that a finite automaton accepts strings and recognizes an entire language. The language that that finite automaton recognizes is the set of all strings that it accepts. That language is regular. And what I mean by that is, there exists a regular grammar that generates all and only the strings of that language. Are you with me? And all that same crap I said, true with regular expressions as well. Take any regular expression, the set of strings that matches that regular expression is a regular language. In other words, there exists a regular grammar that generates all and only the strings of that language, and there exists a finite automaton which recognizes that same language as well. Cool? Okay, so good. We are going to prove all of this next week. But first, a detour into a sort of other topic which we need. Yeah, don't do that. Which we need. And it turns out that though we could do this with finite automaton, it's much easier if we allow ourselves a slightly more powerful kind of automaton, which it turns out is like actually not more powerful. Okay, and we call these non-deterministic finite automata. Alright, so what's up with this? Oh, and these are affectionately known as NFAs. And they are to be distinguished from the other kinds of finite automata by, you call those DFAs, deterministic finite automata. Alright, what is a non-deterministic finite automaton? It's just like a machine, just like before, but now we build some like non-determinism into the machine. And by that I mean, there is no longer a single thing that you do, given a particular state that you're in and a particular input. Now, sometimes you do like multiple things at once. Slash, you kind of do all the things. Alright, so let me give an example, and we'll work through this example, and then we'll like understand what's going on. Oh, okay, so first, a machine. Here's how this machine works. I start in state S1, and in state S1 I have like a, and someone kind of vaguely confirm that I'm staying in frame at all times. I have state S1, and I stay there like processing A and B forever. My language is AB, by the way. But also, if I'm in state S1 and I read a B, I should go to state S2. Whoa. Which do I do when I'm in state S1 and a B comes? Both. Alright, now here's another crazy thing. When I'm in state S2, if I read an A, I go to state S3. But also, I can just like go straight to S3. So this lambda, and maybe it's unfortunate that we're using the same symbol here, but it's really like saying a different kind of thing. It's saying that you may proceed directly from state S2 to state S3 without reading any characters at all from your input. Alright, and now in state S3, if I read a B, I go to S4, and S4 is my accept state, and once I'm there forever. Okay, so this is a sort of a relaxation or an expansion of the deterministic finite automaton in several ways. I think there are three respects in which something new is happening here. The one is the one I already mentioned, that now in a particular state and a particular character is being read next, there are now possibly like multiple states that we go to. So that's like strange thing number one. Strange thing number two is that you can just immediately transition from one state to another without reading any input. And strange thing number three is sometimes there are just no directions for what to do when you're in a particular state. For example, if I'm in state S2 and I read a B, like nothing happens. I can't read a B, so it just dies. And same thing here. If I'm in state S3 and I read an A, I just die. Alright, so to really understand what's going on, we should try to trace through what happens given some kind of input. So take the input A, B, A, B, B, A. And let's like track what happens to this thing. Okay, well, I start in state S1, and immediately to the right of the state that I'm in, I will mention the characters left to process. So here I haven't processed any characters yet, so that's ABA, BBA. Okay. Alright, and now, well, what's the first thing that happens? In the beginning it's like pretty chill, right? I read an A and I go to state S1. Alright, so I am still in state S1 and the characters left to process are BA, BBA. Alright, good. Now, things get weird. Because now, I am about to read a B character. But I have two directions for what to do with B. So what I do is like both. You can think of it as the machine copies itself into two separate machines and follows at both paths simultaneously. Alright, so let's indicate that. So here are some arrows. I go to state S1, and I have read this B, so what remains is A, B, B, A. And on the other hand, I go to state S2, and I've also read a B, so I'm in A, B, B, A. Okay, but another weird thing happens, which is, whenever I'm in state 2, I automatically get a free pass to state 3. So this machine copies itself again, and I sort of like, it's called a Lambda Transition, people call it, to state S3. So I'm going to indicate that with a horizontal arrow because I would like to preserve like the depth of the tree as being the number of characters processed so far. You with me? All right. So now we have three machines reading the same input. Let's see what each of them does. All right. Well, if I'm in state S1 and I read an A, uncontroversial. I'm still in S1 and I have BBA left. Still making sense? I'm going kind of fast, but I think it's fine. Whew. All right, now what happens? Oh, damn, I need to like split again, right? So let's do it. So I split into, I go to S1 and I have BA left, and I go to S2 and I have just BA left, and I also transition to S3 with the BA left. Cool. Okay, let's do some of these ones over here first. What happens in S3 when I read a B? I go to S4 and I have only an A left to read. And then I read that A, and now I'm just like in S4 and I just like accept. So it worked. If I'm in S2 and I read a B, what happens? You just die, yeah, because in S2 there is no rule about what to do when I read a B. So this machine just dies. Okay, what about if I'm in S1, about to read a B? Well, again, I need to split into two separate cases. There's the case where I read in S1, I stay in S1, and there's an A left, and there's the case where I go to S2, and there's an A left, and that automatically also transitions to S3 with an A left. Guys following this? Okay, if I'm in S3 and I read an A, what happens? Die. There's no rule as to what to do when I'm in S3 and read an A. What about if I'm in S2 and I read an A? I go to S3. But now, I have no more input left to process. So what happens? We just, yeah, we also, I guess you could also think of that as a die in the sense that we reject the string, right? Because we finished processing the string in a non-accept state. Okay, and same thing S1A, I go to S1 and I now reject the string. I think I want a different notation here than die, because the machine's not dying due to having no direction. It just ends in S3 and it's not an acceptance.
Just end there.
We can do a frowny face. The frowny face indicates that we do not accept the string. Okay, continuing over here, S2, what happens? If I read an A, what happens? I go to S3, right? And in S3 I have a BBA. Yeah. And now I read that B, and I go to S4 with a BA. And now I process that B, I'm still in S4 with an A, and now I'm still in S4 and I like accept. And in S3, this just dies because there's no rule for what to do in S3 when I read an A. Alright, so this machine branched into like many different machines. I guess I count for every like leaf of the tree is like a different branch, right? So 1, 2, 3, 4, 5, 6, 7 branches of this tree. In 3 of those branches, the machine died due to lack of direction of what to do next. In 2 of those branches, we merely finished processing the string in a non-accept state. But in 2 of the branches, like we accepted the string. And we define the acceptance of a string in an NFA by if any branch leads to an accept state. So if they're